Okay, so in this section, we're going to be solving systems of equations in three variables. Now, there are a lot of similarities with the problems that we did in the previous section where we had systems in two variables. Right? Now, when we had in two variables, right, we solved two equations, two variables in the Cartesian plane, right, and those happen to be lines. Okay. Right, now what we're going to look at here, right, is in three variables. Okay, so the extension here is we're in that extra variable, and we'll have a third equation to go along with it, right, is we're in three-dimensional space, right? And think of the screen that you're watching this, if that's the XY plane, the Z plane is kind of coming at you, right, directly away from the screen, right? So we're in a space and not necessarily a plane. Okay, so just to give you some geometric kind of picture, and I'll show you some graphs in a second. There's a good 3D grapher that we can plug in equations in three variables to get an idea of what these look like. Right now, as it turns out, these equations in three variables, they're what we call they're linear. Now, not linear in the sense that they're lines, but linear in a mathematical sense when each one of those variables, x, y, and z, has a power of exactly 1. All right, so there are linear equations, and these represent a plane in three-dimensional space. Now, there's a lot of similarities with how we solve equations in two variables and in three variables. All right, so for instance, here we'll develop techniques later in this section, but for now we just want to kind of look at some examples and look at some graphs to see what it is that we're solving, just to get an intuition for the types of problems that we have. So let's say that I want to check if 3, -2, 1 is a solution to the system. Okay, excuse me. So similar to equations in two variables, right? In order for something to be a solution, right? Notice one difference here is we have an ordered triple instead of an ordered pair. Think of these coordinates to be x, y, and z, right? So we have an ordered triple instead of an ordered pair. So I need the ordered triple to satisfy all three of these equations. And so let's say if I number these 1, 2, 3. So I'll start with equation 1. So I'll take this ordered triple 3, -2, 1, and I'll plug that into my equation 3, -2, 1. And then we see 3 minus 2 is 1, 1 plus 1 is 2. So we get 2 equals 2. So that checks out. All right, so let's take a look at 2. All right, so we plug in 6 times 3 minus 4 times -2 plus 5 times 1, and that equals to 31. And here we have 18 plus 8 plus 5 is equal to 31. So 18 plus 8 gives me 26, and then we add 5 to that, so we get 31 equals to 31. So that checks out. Okay. All right. Now keep in mind, right, this is not enough to show that something is a solution. Right, it needs to satisfy all three of them. So for the third one, we have 5 times 3 plus 2 times -2 plus 2 times 1 equals to 13. So we get 15 minus 4 plus 2 equals to 13. And here we have 11 plus 2 is 13, does in fact equal to 13. So that checks out. All right, so now we can say, right, with the evidence that we have in front of us, that 3, -2, 1 is a solution. Is a solution to the system. All right, now I'm going to show you some graphs here of what we're looking at. The first one being is of the equations that we just saw, right? And again, notice here we have those equations each represent a plane in my three-dimensional space, right? You can see the three coordinate axes, right? That excuse me, that blue axes, right, coming up here is the z-axis, and the other two are our x and y axes, right? But again, let's focus here. We have the three equations of the plane, and then what you see we have plotted there, 3, -2, 1, is our solution, right? And notice that at that point, all three of the planes are intersecting, all right, giving me that unique solution. And there is no other solution. There is no other point where that happens. All right, now we see here that in certain areas, right, 2 of the planes intersect at the same time, right, but never all 3. All 3 intersect here, giving us a unique solution. All right. Now, if you recall from the previous section, we had 2 variables, right? There was different things that could happen, right? We either had a consistent system, which gave us a solution. We had an inconsistent system, which gave us a no solution. But we also had the dependent ones, where it was the exact same line, right? So as it turns out here, there are similar situations that happens when we are working with 3 variables, right? So here we have our coordinate axes, excuse me. All right, and now here I have pre-graphed 3 planes here, right? And what I want you to notice here, these would correspond to planes that are inconsistent, right? They don't have a solution, right? And we can see the reason they don't have a solution. Here we go. So if we look kind of side view here, right? Now, one thing to keep in mind that, it's a graph generated on this software system. These planes stretch out infinitely in every single direction, right? They're flat, kind of like, think of like a piece of paper, right? But they would extend out to infinity in every single direction. So we have kind of a side view here, right? And you can see what these 3 planes are doing. Right now, a system like this is an inconsistent system. Right now, the reason it's inconsistent is even though we do have some intersection with the planes, it's never all 3 at the same time. Right? If I take them pairwise, excuse me, whatever pair I decide to choose, right, they intersect. Right? But not as a whole system. Right? In order for them to be to have a solution, all 3 of them need to intersect, right? Like they did in the previous one at that one specific point. So here's an example of an inconsistent system where 2 of them at a time intersect, but not the 3 as a whole. So something like this would be inconsistent. So let's take a look at another system. Now, if you look here, right, this is kind of similar to when we had parallel lines and they never intersected. And that was what we call inconsistent, right? There was no solution here. So this is a very similar thing that's happened, except now we're looking at planes instead of lines, right? Where we have no intersection between any of them, right? These are in fact parallel planes. Okay, so this system would also be inconsistent, right? Where we have no type of intersection here. Now, the third thing that can happen here is that we do have a system that is consistent, but it is dependent. In other words, that they intersect at more than one point. And what we're going to find out is that the 3 planes are either going to intersect at one point, all 3 are not going to have a common intersection, or they'll all intersect at an infinite number of points, right? And that infinite number of points being a line, right? So if we look at this third system here, now these do have points in common, right? But it's different than the previous one in that it's not one in common, right? They actually all 3 kind of intersect at a line, right? This isn't the one where it's piece two at a time intersect. They all three, in fact, do intersect at a common points, and that point being a line, right? If I graph this line, we see here that point lies on all three of those. Sorry for the jerky movement here. On all three of those planes. And this is an example of a dependent system. Okay, so what we're going to look forward to in this section is, how do I know in which state I'm in, right? Am I in the unique solution, no solution, or infinite number solution? And we'll develop techniques to help us algebraically determine that.